So yesterday we started 11.2. Okay, we looked at the finite series. Main things that we did in that section, we learned about sigma notation, how to simplify sigma notation under certain conditions, specifically if you're adding up constants, integers, perfect squares, or perfect cubes. And I also showed you the formula for simplifying or finding the sum of a finite geometric sequence. So we're going to look at, today, adding up an infinite amount of numbers. So at first it might not make sense, like how can you add up infinitely many numbers? Well, we technically you can, but you can approach a value, or you can have a limit of what you would get close to. And that's what we're going to look at. So there are some series that when you add up every term, you get an answer, or you get very close to an answer, and there are some that you can't. So if I were to take a series like this, that goes on forever, and I were to try to add up every number in this sequence, what would happen? Yep.
Well, like, there would be like a lot of numbers to add. First of all, like, second of all, like, I guess it would just infinitely just like grow. It wouldn't be stopped by anything. It wouldn't be limited by anything. It's just with enough time, it could technically be like any number, like basically positive infinity.
Okay, so that's two different things, saying it approaches a number versus approaching positive infinity.
It approaches positive infinity.
Yes, there is no number that approaches. It does approach positive infinity. So what kind of sequence could you have, what kind of sequence do you think you could have, where you could add up infinitely many numbers and get an answer that doesn't approach positive infinity? It's not a sequence like that. That wouldn't work. Yeah?
Maybe one that alternates between positive and negative, like where it goes back and forth.
Alternating between positive and negative?
Like if it goes from like 1 to negative 1.5, to positive 1.5.
Okay, so maybe, yeah, I think you could have something that would alternate, and it might add up to something. Yeah. To think about it a little bit more, because it's not what I was thinking of, but it seems like that potentially could work. Anyone have another guess? How about between arithmetic and geometric? What type of sequence? Bless you. What kind of sequence do you think would work for adding up an infinite amount of terms and getting an answer? An arithmetic or geometric? A geometric. You can never add up infinitely many terms in an arithmetic sequence. It'll never work. Okay? The only type of sequence that could work is geometric. So this is the notation for an infinite summation. The big difference from the notation yesterday is the sigma has an infinity symbol at the top, and when you write it in expanded notation, you have a dot 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 on the end. We didn't have a dot 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 on the end yesterday. When you expand out the sigma notation, generally what I do is write the first couple terms, then dot dot dot, and then there'd be an nth term at some point later on, and could be the 700th term. But then there's even more terms after that. Okay, so if you weren't here yesterday, I explained all what this notation means. So you'll have to go back and take a look at that. So adding up an infinite amount of numbers is obviously not possible. All right, so directly calculating the sum of an infinite amount of things, it's not going to work. So we got to come up with a different way of thinking about it. Okay. So there's really two approaches we can look at. We can look at it graphically, and kind of look at, are we getting close to something but never reaching it? And if we are getting close to a number and never reaching it, that would give us a pretty good idea of what these numbers would add up to. What do you call, like when you graph something you get close to but you don't reach it? Yeah? Yeah, an asymptote. So if an infinite amount of numbers are going to add up to something, visually, you're going to see an asymptote. The sums are going to get closer and closer and closer and closer. And that's kind of what we're going to talk about right now. So let's say that there is some number. Okay, I'm just going to call that number S. And when you draw the line y equals S, that line is an asymptote. That asymptote is basically what your sequence is going to converge to. Okay. That's the term that we use when an infinite amount of terms is going to add up to something. We say that the sequence is converging to that number. All right, so if you had a sequence like, let's say you had terms, let me think for a second, like 1 plus 1/2 plus 1/4, and so on. If you were to add up every term from 1 to infinity, in that sequence I wrote down, it would add up to 2. Okay, all these numbers would add up to 2. So if I could find a formula for that, graph it on the calculator, that formula would have a horizontal asymptote at the number 2. Right, so we would say that this sequence is converging to the number 2. Now, something I want you to be careful about that people mess up on the test. There's a difference between what the sum of these terms is converging to and what the individual terms are approaching as you continue forever. The sum of the terms is approaching 2. But what is each individual term getting closer to? 0. Very different questions. In order to be able to add up infinitely many numbers, the individual terms themselves have to be approaching 0 as you head to the right. Okay. Yes?
Like it might just be that my brain's not working, but like you said, if you had all of them to like infinity, it would equal 2.
This would add up to 2.
That doesn't make sense because like it can't like be.
Well, it would converge to 2.
That doesn't make sense. Like I thought the closest like you could get would be like maybe 1.9 repeating for like 1.9 repeating.
Right,
So,
it would converge to 2. So the term converge basically means it's like a limit.
so hypothetically, if you could do it infinitely, like actually do it infinitely, it would happen. But in the real world, if you got to the millionth term in that sequence, we would actually get with 1.9 like thousand nines.
Yeah. So what we're looking at here is we're saying that it converges to 2 as the number of things you add up approaches infinity.
But you can't actually reach that in the real world.
Correct, because you can't reach infinity. So it's approaching. Okay? It's converging to the number. I'm not saying that it will equal the number. So a little bit of difference there.
Thank you.
Yep. All right, so any question on that idea? That's kind of a visual way to think about it. And remember, when you graph a sequence, is it connected or not connected?
Okay.
It's not connected. It would just be dots. So when I say it's going to approach an asymptote, it's not going to look like this. It's not going to be connected. It would just be these individual terms that are getting closer. So you just see dots. Okay. So again, technically, an infinite series, it's not really a sum. okay? Because we can't add up infinitely many things. We're basically looking at a partial sum, but we're going to go as far out as we can imagine, okay? So partial sums, like this represents adding up the first 1 terms. That's like the first 4 terms. What we're going to pretend like we're doing is we're going to look at like if we added up the first billion terms, okay? Because that's pretty close for our purposes to infinity. We're going to look at what the partial sum way out would be. And that's going to be a good approximation if we could go to infinity, what the value would be. And in fact, sometimes we don't even need to go that far out. Sometimes if you just add up like the first 5 terms or 6 terms, you can already tell what it's going to be. Like you might add up the first 5 terms and you get 1.9993. Well, if I added up 5 terms and they added up to 1.9993, it's probably going to add up to 2 if I could go to infinity. So sometimes it doesn't have to be that far out, really. All right, so that's the expansion of a infinite geometric series, kind of written in a general way. So this is the value you start at. This is the value you stop at.
So start is k equals 1.
Yep, we're starting at 1 because 1 is the position of the first item in the sequence. Everything always starts with position 1. And then what's happening as I'm going down is I'm just plugging in higher and higher numbers for k. So the first term in the sequence is just the a sub 1, just the first term. The second term in the sequence is when we plug in a 2 right there. 2 minus 1 is 1. And then we get r to the first. And what basically happens is the exponent goes up on r by 1 each time. So if I was going to write down the third term, it would be if I plug in a 3 right here. A sub 1, r squared. A sub 1, r cubed would be the next one. A sub 1, r to the 4th. A sub 1, r to the 5th. And that pattern is going to continue forever. Notice that this is the position. The exponent on your r is always 1 less than the position that you're in because of that minus 1 right there. So when you get all the way to the nth spot, the exponent will be 1 less than that. So if I was in like the 30th spot, what would be my exponent on r?
29.
It would be 29. A sub 1, r to the 29. And you can see that by putting in a 30 right here for k. It would be 29. Okay. And why do I have a dot, dot, dot at the end? Because of that right there. Yep. All right, so let's try, we'll try an example. And all that we know right now is the formula for adding up a finite amount of geometric terms. Well, we could use that to basically figure out an infinite amount. Right? So let's try. So I want to add up all the terms from 1 to infinity in the sequence that generates, in the numbers that would be generated by that formula right there. Okay. Can someone remind me from yesterday, what's the formula for the sum of a finite geometric series? We did 2 in the homework, and they're the ones I said don't leave the fraction within the fraction. Yep.
Is it Sn equals a1 times 1 minus
R squared. R to the
1 minus r over n. Oh yeah, over 1 minus r.
Okay, so that's the formula. So that's not adding up infinitely many. That's adding up a certain number. But let's try doing this problem by adding up the first 4, the first 5, and then the first 6. And let's see if we notice a pattern of what we're getting close to. Okay, so I already did the first 4. I filled in a sub 1 is my first term. R, so that's a sub 1, bless you, and that's R. Okay, because I know this is a geometric series. And when you write a geometric series, the R is always the number that's in parentheses, and a sub 1 is always the number that's in front of the parentheses. Okay, so I filled in 2 1/3 into that formula, and I got 2.96. Now, just adding up the first 4 in this pattern, I'm already getting pretty close to a number. Okay, let me show you what that formula is doing in case it doesn't make sense or you weren't here yesterday. Let's find the first 4 terms in this pattern and add them up by hand and see if it gives us 2.96. If you plug in 1 for k, what would you get
1.
in what's circled in red?
You would get 1 because anything to the 0th power is 1. 2.
Times 2. Yep. So you get a 2. All right. Let's do the next term. So we plug in a 2. What's 2 minus 1? 1. What's 1/3 to the first?
1/3.
1/3, and 1/3 times 2?
2/3.
2/3. Okay. Now we're going to plug in a 3. What's 3 minus 1?
2.
2. What's 1/3 squared?
1/9.
And what's 2 times a ninth? 2 ninths. You can probably see the pattern. The denominator is just being multiplied by 3. Those are the first 4 terms in that sequence. Let's add those up and see if we get 2.96. Okay. That, in theory, is what this formula is doing for us automatically. Okay, so let's take 2 plus 2/3 plus 2 ninths plus 2 27ths. Okay, did I type everything in right? I think that looks good. There you go, 2.96. Okay. So now, rather than keep figuring out all these terms and adding them up, let's do the first 5. What's the only thing that would change in this formula if you want to add up the first 5 terms? Yep.
The exponent.
Yeah, the exponent becomes a 5. If you do that, you get 2.98. So if you figured out the next term here and then added it to what we already have, you'd have 2.98. And if you do the first 6, you get 2.9877. So
Wait.
what do you think we're getting pretty close to? Yeah, we're getting pretty close to 3. Okay, so there's the first 4, the first 5, and the first 6.
So we're going to approach 3, but never actually make it there.
Right, we would say that this summation converges to 3. The other way you could word it is you could say the limit of this summation is 3.
But the sequence is approaching 0.
The individual terms in the sequence are approaching 0. 2, 2/3, 2 ninths, 2 27ths. They're getting smaller and smaller and smaller.
It's odd numbers, they're just getting multiplied by 3.
So just make sure you pay attention to what the question is asking. What are the terms in the sequence approaching? Or what is the sum of the terms in the sequence approaching? Okay, big difference.
How did you say your answer would be if you're going to say limit?
So we could say that the limit of this example is 3.
Thank you.
Yep. The limit, and then you could write the limit of the sum from 1 equals infinity of 2 times 1/3 to the k minus 1 is 3. Yep. Right now, let's visualize that. Okay, so to visualize it, what I need to do is I need to type in this formula so that these values can be generated for me automatically. All I'm going to do is, instead of filling in a specific number for the exponent, leave it as x. And then on the calculator, you can let this be any number you want. 4, 5, 6, doesn't matter.
So just on a regular, like, not the polar axis, not the other axis, just like the y, well, it's supposed to be that one.
So we're going to type this in on y equals.
Yeah.
So we're going to type in 1 minus, well, 2. Let's start with that. 2 times, I might need an extra parenthesis, I'm not sure. 2 times 1 minus 1/3. But I'm not going to raise it to the 4th or the 5th or the 6th. I'm going to raise it to the x. And by doing that, I can let the exponent be anything I want now. Now, it only makes sense for the exponent to be what kind of values?
It has to be integer.
It has to be positive integers. If you plug in a decimal, will it give you an answer? Sure. It just doesn't make sense in this problem. Okay. All right, so there's the numerator, 1 minus 1/3 to the x. And now the denominator, we could simplify. What's 1 minus 1/3?
2/3.
Yeah, so the denominator is always 2/3. So we're going to do divided by 2/3. I'm trying to decide. I think I want an extra set of parentheses. Let's go like that. And like that. Might not need it. I didn't mean to overwrite that. I tried to put in extra parentheses. Alright, so it's going to do the numerator, it's going to do the denominator, divide them, and then there's a 2 in front of everything. Okay. I can check if we did it right by going to the table. Okay. If you add up just the first term in this sequence, you get 2. If you add up the first 2 terms, you get 2 1/3. If you do the first 4 terms, that is my 2.96, 2.9877, and so on. So now this table is showing me what they add up to. Let's graph it. What is it? What are the only numbers that make sense for the exponent?
Positive integers.
Positive integers. So let's start at 1, and we'll add up the first 10. We already know it's not adding up to a negative number. It is possible. You could add up to a negative, but we're not in this case. What does it look like we're adding up to?
3.
3. So I'm going to go to 4. Okay, I'm going to hit graph. And what you're looking at there, that's a visualization of the sums. But you shouldn't be focusing on the values in between the integers. Just these. That's what you get if you add up the first term, first 2, first 3, first 4. And we can see what's happening. It looks like we're getting an asymptote at the number 3. And if we are getting an asymptote at the number 3, then that is what this series converges to. And it is. The answer is 3. All right, so that's how you could visualize the summations. Any question on that? And once you get out, even I think probably, yeah, once you get probably a little bit past the first 10 terms, the calculator is going to run out of decimals, and it's just going to say they add up to 3. Remember, you can highlight it, and you can get more accuracy than it shows. But once you go beyond 4 decimals in the table, it just rounds it. All right. So that's actually what I just did. So I graphed that on the calculator, and look at what happens as x gets bigger and bigger. As x gets bigger and bigger, we're approaching the value 3. Let's try this one. Let's find the sum using a graphical approach. Since I already have it typed in from the last problem, actually we did that one. Let's do this one. Find the sum using a graphical approach. I already have it typed in from when we did example 2. Okay, we've already done example 2. So I'm just going to change the numbers to match example 3. Okay. What's the first term in example 3? Yep, 4. You can see that if you don't see it, plug in 1 for k, and you'll get 3 to the 0 times 4. That's 4. What's our r value? Yep, 3. So the r value is what we multiply by each time to get from one term to the next. What do you think is going to happen if instead of multiplying our terms by 1/3, we multiply the ones that we're going to keep adding together by 3 each time? Anyone have an idea what's going to happen? So what if to generate the next term in the sequence, we multiply the previous one by 3 and then add it? So we're going to multiply the one we had by 3, add it. Then we're going to multiply that one by 3, add it in, and then multiply that one by 3. So we're going to keep multiplying the next term by 3 each time. What's going to happen if we add all those up? Well, what did we multiply by last time when we did example 2? Let's see. What did we multiply by each time in example 2? Yeah? 1/3. Because we multiplied by 1/3 each time, that caused the individual terms to approach what? Approach 0. So now we're multiplying the terms by 3 each time. So what are the individual terms going to approach? Yeah? They're going to approach infinity. And what's going to happen if we add up a bunch of terms that are approaching infinity?
It's also
That's also going to approach infinity. So let's type it in. We already know what's going to happen, but let's see what it looks like. So we have 4 in the front, and we have 1 minus r is 3 this time. I've got extra parentheses, but I'm just going to leave them.
the bottom one will be -2.
And the bottom would be 1 minus r, which is 1 minus 3. So make the bottom -2. Again, I do have some extra parentheses, but that's okay. So a sub 1, 1 minus r to the n over 1 minus r. Okay, so we already know the first term in the sequence is 4. Just to make sure we did this right, what's the second term?
Second term is going to be 12.
12. And what's the third term?
36.
Okay. You add up the first term in this sequence, what do you get?
16.
You get
4.
4.
Yeah.
What if you add up the first 2?
16.
And then the first 3?
52.
Uh,
It's going to be 16 plus 36, which is 52. Let's see if I go to the table, if I get 4, 16, 52. If I do, then we typed it in right. 4, 16, 52. So look at what's happening to the sums as you add up more and more terms. Does it look like those sums are approaching a number?
No.
No, they're approaching infinity. So this one, the sum was 3. This one, find the sum. I'm just going to say this does not converge. So when they say find the sum, they are looking for a number. Infinity is not a number. So what makes this one converge and what makes this one, you're going to learn the word in a second, diverge? Is it because this one was a 2 and this one was a 4? Yeah.
Because of the fraction?
And what is that? That's the,
I forgot what R is called.
well, yeah, it's just the r value.
Yeah.
So it has to do with the r value. So what kind of r value do you think would allow us to converge and what kind of r value would cause us to diverge? Yep.
any R value that is less than 1 or greater than 0 will cause it to converge.
Less than 1 and greater than 0.
It
Okay.
needs to be in between those because we can't have anything that's 0 or less than 0 for this. Well,
Could we have something? Let me just check something real quick. Yeah. Could we have a number less than 0 and have it still converge?
it has to be between these 2 points. It needs to be -1 to 0, not including those 2 points, and then 0 and 1, not including those 2. It has to be anything that's in between them.
Could you include 0? You could include 0 and it would still converge. If you put a 0 here, if that's the number 0, then 0 to any power is always 0. So you'd just be adding up a bunch of zeros in that case, which is okay. That does converge to 0. So the key thing about R is it has to be between -1 and 1. If you multiply repeatedly any number you can think of by something between -1 and 1, it's going to get closer and closer to 0. Okay, take the number 78, multiply by 0.57. If you keep multiplying by 0.57, because 0.57 is between -1 and 1, each time it's getting closer and closer to 0. Okay? If you multiply by something bigger than 1 or smaller than -1, that's going to cause your number to grow, and that's when it's going to diverge. Okay? So sometimes a geometric series converges, sometimes it diverges. Yeah.
I was thinking like for the positive and negative, that like negative fractions could do like the exact same thing where like it reaches 0 but it never touches it, or where it reaches like a certain number of like that example we had about the positive 3. We have an example where it reaches -3 but it doesn't actually like reach it.
So yep, if you multiply by a negative number like -0.21, what's going to happen in this case is it's going to still converge to 0. It's just going to oscillate between positive and negative as it does it. Okay, so if I multiply by -2.1, I get -8.4, positive 1.7, -0.3, positive 0.07. It's still going to 0, it's just kind of oscillating as it does it.
And that's why it's important that it's dots and not aligned, because for it to be aligned, it would say that would mean it reaches 0 because it's technically going through the axis. But since it's points, there's not a point on the 0 axis.
No, it never really hits it, it just bounces around it.
Yeah.
All right, so if we had, okay, that's the formula for adding up a finite amount of terms. If R was 0.8 in this formula, would it converge or diverge? This would converge. What about if R was 0.9?
Converge.
That would also converge. Which one would converge faster, A or B? A. So when A would be taking like 80% of the number each time, so it's going to get smaller quicker, right? How about 1.1?
Diverge.
Okay, that would diverge. And what about 1.2? Yeah, that would also diverge. Which one would diverge faster, C or D?
D.
Yeah, D, because it's going to get bigger quicker. What if R was exactly 1?
Neither. Well,
What do you think?
diverge.
They
But-
make the same as 0, except
Because if converging means you're getting closer and diverging means you're getting farther away, like as long as you're not,
Oh wait, it's
as long as you're just multiplying by like a number and it's not like a millionth of a decimal point away, that's technically diverging because you're still getting the same distance away.
So what's going to happen here if this is a sub 1, r to the n minus 1? When you raise 1 to a power, let's start with the first term.
1.
1 minus 1 is 0. What's 1 to the 0?
1.
1 times 4?
1. 4.
4. So here's your first term. Okay, second term. What's 2 minus 1?
1.
1. What's 1 to the 1?
1.
1 times 4 is 4. So what you're going to get here is a sequence of 4s that are repeating. Same number. Is that going to be converging or diverging when you add them up? That's diverging. Okay, it's still diverging because you're going to be adding them up and it's going to approach infinity. Okay, it's not going to add up to a number if you keep adding up 4s over and over. So that's why when I talk about what converges and what diverges, if it fits that criteria, the absolute value of r is less than 1, it will converge. Right. So visually what that would mean is you'd be looking at something like this. Here's your number line. If you want to shade in all the values that are going to cause it to converge, it's from here to there. The black section is converge. And here is diverge and diverge. Put a decimal. I only eliminated writing one letter in the abbreviation, so I'll just put the E. So diverge. So now what I want to do is kind of think, what would the formula be without having to use this one? Because this is really for a finite series. And we just have been pretending like x gets really, really big. Well, we don't even really have to do that. We can come up with a simpler formula. Let's think about what would happen in this formula if r is somewhere in this black section. R is a value that would cause you to converge. So think of an R value that would cause you to converge. What would be a value? Yeah? 0.5. So if you plug that in the bottom, well, it's just 1 minus 0.5, whatever that, 0.5. But I'm interested in what happens right here as n gets really big. So if you take like 0.5 and raise it to, what's a really big value?
100 trillion.
100, okay, 1,000. If you take 0.5, which is a value that would converge, and raise it to the 1,000th power, what's 0.5 to the 1,000th power getting close to?
Really, really small number is 0.
It's getting really, really close to 0. So as the exponent gets really big, this part that's circled gets really small and it gets close to 0. If we're subtracting something that's basically becoming 0, we don't need it. Okay? And the bigger and bigger that this exponent gets, the less and less significant this becomes. Right?
If we put it in the calculator for that, it literally just says 0.
Yeah, it's very, 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 very small.
It's too small, but if we do 100, it does say like.
So as n goes to infinity, this formula can be simplified. We don't need this part anymore. It doesn't matter because it's approaching 0. So now we have this, a sub 1 times 1 over 1 minus r. And if I put that together as one fraction, what would it be?
A1 over 1 minus r.
Yep. A1 over 1 minus r. And that is what happens as n approaches infinity in that formula. And that is the formula for adding up infinitely many terms in a geometric sequence. It's simpler than the formula we learned yesterday, even though you're adding up even more. So let's try that formula on this problem. Okay, and I'll label what that is. So that's the sum of an infinite geometric series. It's the sum of an infinite geometric series. Now, if R isn't a value that would cause you to converge, this formula doesn't make sense. It doesn't. I mean, you could plug R in, but it doesn't do anything. Okay, R has to be a value that would converge. Okay, so let's look at this one. What's the R value in this one?
1/2.
1/2. Is that a value that would cause your terms to approach 0?
Yes.
Yeah, so if the terms are going to approach 0, then I can add them all up and give you an answer. Okay, so we know R is 1/2. What's my first term?
A1 is 5.
A1 is 5. Let's plug those into the formula for the sum of an infinite geometric series. 5 over 1 minus 1/2. What is that going to come out to?
10.
10, yes. So if you were to list out every number in this sequence and add them all up, all the way to infinity, they would add up to 10. They would approach 10. That's pretty much the end of 11.2. Yeah.
So to clarify, that formula just tells us what the sequence will add up to after.
This tells you what the sum, as long as it's geometric, it tells you what the sum of an infinite geometric sequence would add up to. Yep. So if we go back, a sub 1 over 1 minus r, look at the first problem we did. We got that the answer here was 3. What's the first term in this one?
4. Sorry. Wow.
First term is 2.
2. And what was the r value?
The R value is 1/3.
R value is 1/3. So that's 2 over, what's 1 minus 1/3?
2/3.
2/3.
So that would be
6 halves, so 3.
2 times 3 halves, which is 6 halves, or 3. So this formula gives us the same answer that we got by kind of experimenting and just looking at a table. But now, we don't even have to go through and look at a table or even look at a graph like that. Okay, we don't have to find S4, S5, and S6 and look at the pattern. We got a formula to find the answer right away. Yep.
For that series of like 4, 6, can you go like back one? Yeah. 4, 6, 12, 36. What's that from?
I think that was example 3.
Okay, thanks.
I just had more space over here. Okay, that one doesn't converge because the R value is 3. It doesn't converge.
It diverges.
It diverges, yep. So on the test, the wording you could see for one of these questions is find the limit of the sum if it exists, and then if it does exist, tell me the number that it approaches. All right. So in this one, you would say the limit of this summation exists, and it is 3. It converges to 3. On this one, you would just say this one does not have a limit. It does not converge. So you can't find the number because it doesn't converge. All right. Any question on that? So looking at example 4, what if I asked you, what do the individual terms in the sequence 5 times 1/2 to the k minus 1 approach? What are the terms?
0.
The terms in that sequence are approaching 0. What if I asked you, what are the sum of the terms in that sequence approaching? 10. Yes. Approaching 10. Okay. And I will ask both those kinds of questions on the test. Yep.
What is K for these problems?
K? K is the index on the summation. So it's telling you the number that you plug in to that formula to generate a specific term. So when K is 1, you're generating the first term. When K is 10, you're generating the 10th term. When k is infinity, you're generating the infinite term.
I thought it was like, so k can only be integers once, so 1, 2, 3, 4, 5.
Right.
And so like the thing underneath the sigma thing for the Greek letter, that's the first term, and then the thing above the sigma is technically like the final term.
It's
So
what you plug in to get the first term and what you plug in to get the final term.
Okay.
And you can also reindex the summation. It doesn't have to start with 1. It can start with another number like 0, and I talked about that yesterday. We generally don't do a lot of reindexing with this stuff, but we talked a little about it in yesterday's video.
Would there be a question on the test where k isn't 1?
Yeah, you're going to see something where k could be 0, or it could be a different number. It's not going to be in relation to a problem like this one. It's going to be in relation to something we did yesterday. More like, I'll give you a sequence of numbers, and you have to find a pattern. And it might be like a multiple choice. So, like if I gave you one like, let's just say I'll pick a simple sequence. 2, 4, 6, 8.
That's right.
And I said to you, write the following sequence in sigma notation. Well, one way you could do it is you could start at 1. You could stop at 4. And you could use the formula 2k. Because if you plug in 1, what's 2 times 1?
2.
2, there's your first term. Let k be 2. What's 2 times 2? There's your second term. So this is correct for that. Another answer that's also correct is this. I could start at 0 and go to 3. So that went down 1, so that has to go up 1. So 2k plus 2. Let's try that and see if it works. If you plug in 0, what's 2 times 0?
0.
0. And 0 plus 2?
2.
2. There's your first term. Let's try the last term. Let's plug in 3. What's 2 times 3?
6.
And 6 plus 2?
8.
8. Your last term. So that's an example of reindexing a sum. It's still the same thing. The reason you'll have to know how to do that is because I could give you one in the test where I start with 9. I could start with any number. 1 and 0 are the most common. Right? But you should have an idea of how to do that. Yeah?
So the number on top, like 4, 3, tells you just how many terms there, or how many, like, you can plug in until you get to the end of the sequence.
Well, so the number on top here is 3, but there's 4 terms in that sequence. So I guess if you take the number on top minus the number on the bottom and add 1 to it, it would always give you the number of terms. 3 minus 0 is 3, plus 1 is 4.
4 minus 1 is 3.
Plus 1 is 4. So yeah, I guess if you took that number minus that number plus 1, it would give you how many you're adding up. Yeah. Yep.
So the thing that doesn't make sense to me is like, I thought that the thing on top of the Greek letter was like the upper limit. So you can only, like for the first one, you can only go up to the 4th term, which is 8. And
You
so
can
that-
only go up to plugging in the number 4 for k. This is not a position number. This is a number you plug into a formula to get a value.
So what means position then?
Well, nothing really means position here. It just means this is the number you plug in to this formula to get a result. So 0 is the number you plug in to get the first position. 1 is the number you plug in to get the second position in this problem. So this number doesn't indicate the position. It's not, because there's no such thing as the 0th position. Right? It's the number you plug in to get the value in the position. If you start at 1, then yes, the number that you're plugging in is also the position that you're finding. So you're plugging in a 1, you're finding position 1. Plugging in a 2, you're finding position 2. Plug in a 3, you're finding position 3.
Well, you could.
But over here, you're plugging in a 0, and you're finding position 1.
But
Plugging in a 1, you're finding position 2.
you couldn't use either of those four. I mean, you couldn't plug in. You couldn't use those to prove like 10 is a part of those series because that surpasses the upper limits of the terms you can put in, because like following that series, you know it's +2, say +2 is 10, but you can't like prove that using either the formulas, right? Because that'd be surpassing like the limit of 4 times 2 is 8, or the limit of 2 times 3, 6 plus 2, which is also 8. But like you can't prove 10 using either of those, right? Basically, it goes up. The thing we have written down is up to 8, and so
Right,
if you
you
wanted to
can't,
prove
10 doesn't exist. We're gonna pretend that number doesn't even exist in this world. The only numbers that exist are 2, 4, 6, and 8. We can't go beyond that before it. We can't go after it. Those are the only 4 numbers. There's no 10 in this at all.
okay.
Okay. Any other questions on that? Okay.
Can K be negative?
No. Well, what do you mean? The index, or what do you?
Just
the,
K.
The
Just
number
K.
on the bottom?
Yeah, the number on the bottom.
Yeah, it could be a negative. Because remember, that doesn't indicate the position number. It's the number you're plugging in to find something. So sure, I could write. I could make K be negative. Yep. But it cannot be a decimal. Definitely, I've never seen it as a decimal or a fraction, ever.
And then kind of like the question I always ask, do magic like